All right, welcome back. So, in this class, we're going to talk about pointers in C. And pointers are one of those topics that people get nervous about because there's a lot of different ways to think about them and it can feel very confusing. But in some ways, pointers are a relatively straightforward notion and it's a really powerful notion. Assembly language, we use pointers all the time, but we don't call them that, and people usually have an easier time in there. In old versions of BASIC, we had something like pointers. There was a pair of functions called peek and poke. In Fortran, which doesn't have pointers, we found ways to emulate pointers by using arrays. So it's a fundamental concept, and getting a good grasp on what pointers are helps you figure out how to use them. And really, once you've figured out a few examples and understand a few examples really well, everything else is just the same thing over and over again. So to work with pointers, we really need to think about the memory of a computer. And we know, a computer has memory. We store numbers there. We pull numbers out from there. We've got to think about the memory in order to understand what pointers are. And in CSE 222 in winter, most of what we're going to do is work with manipulating the memory of a computer directly by creating things called data structures. So this is a worthwhile exercise to think about not just lines of code in C, but to be also thinking in parallel about what's happening to the memory of our computer. So to help with this, I have here an actual memory from inside a laptop. And each of these locations is one memory location. It stores a small number, 8 bits, so a number between 0 and 255. And each box is identified by another number, which we call its address. So the address of this box is 104. The address of this box is 113. These are just like addresses on houses when you walk down the street. It's a way to identify one box from another. So if you have 16 gigabytes of memory in your computer, there are 16 billion of these boxes sitting inside that little memory card. All right, so what do we do with these boxes, these little containers that can hold information? Well, we use them to store data in our program. So let's look at a sample program. For example, I might declare 3 integers, x, y, and z, and then have a statement that says print the value of x. All right, so I'm going to take some liberties here with what really goes on in the name of simplification. So what I want to have you think about is when you're compiling this program, when you say GCC to take this source code and turn it into an executable program, what actually happens? Now we know that printf means we're going to call some function with a bunch of statements in it that'll figure out how to print the value of a number. But what happens when the compiler sees something like int x? And we don't think of this as doing much. We're not initializing a value here, but we're somehow declaring that x is an integer. So here's what I want you to think of. The compiler decides, okay, x is going to be an integer. I'm going to have to store that somewhere in memory. Where should I store it? And it makes a decision. Now, it's not actually the compiler. It happens in between the compiler and something called the linker, but let's just think of it as a compile operation. So the compiler sees int x. It asks the question, where am I going to store x? And it can store it, anywhere in memory that it has access to. So just for the sake of argument, I'm going to make a little table with the name of a variable and the location where it's stored in the memory. And I'm just going to suppose that the compiler decided x is going to be stored at location 104. So here's another small simplification. I'm using decimal numbers, base 10, for these addresses. Normally, if you've done classes with me, I tend to always work in hexadecimal. But for the sake of not adding extra complexity here, I'm numbering these addresses with decimal numbers. So from 109 we go to 110, 111, 112, and so on, instead of going to 1A, 1B, 1C. So these are decimal numbers. That's what the period represents. So we're compiling this program. The compiler says, okay, I need to store x somewhere. I'm going to store it at location 104. Why 104? I don't know. That's what it decided. it gets to the next statement, which says integer y. Aha, I've got another variable I have to store. It's different from x. I can't store it in the same place as x. Where should I store y? Well, I'll keep it nearby. I'll store it at location 108. All right. And then the last statement here, integer z, well, exactly the same thing. It says, hey, I've got another variable z. I've got to store it somewhere. I've already got something here in 104 and 108. I may as well store z in the next location, which is 112. All right. So in your program, when you see something like the variable x here being used as an argument to a function, we see x, we think of it as an integer. The compiled code sees the number 104. Right? That x basically gets replaced with its address, and there will be something which says, hey, take the contents of this location 104 and pass that to our print function. So we work better as humans with, symbolic names, but those are completely lost by the time the compiled code is handed to the CPU, and the CPU is just thinking in terms of, oh, this is location 104, 108, 112. All right, so what happens when we say print the value of x? Well, a lot of things happen inside this printf routine, but ultimately it has to look at the value of this variable x. Well, how does that work? X is the same as location 104. So some part of the machine will go into memory and say, hey, memory, tell me what's at location 104. So there's a memory management unit. So you say, what's in location 104? And the memory management unit says, okay, let me look. So it looks in that location and sees the number 25. And it comes back and it says, hey, that number is a 25. So our code now sees a 25 right here, and it goes through everything that a print statement is supposed to do, and eventually what does it do? It prints the number 2 followed by the number 5. So if we compile this program and we run it, it might print out 25. Now why did it print a 25? There's no 25 anywhere in here. But there happened to be a 25 sitting here in location 104. There's no reason why that should be a 25, but here's something important to keep in mind. There's no such thing as an empty memory location, right? If I open up this location 121, there's nothing in there. Well, that can never happen, right? There's always some number between 0 and 255 in every one of these memory locations. If we don't put a number in there, there's still a number in there. If you go back to Engineering 250, when you have a flip-flop always has a value on its Q output. It's 1 or 0. If you say this, then it becomes a 1. If you say that, it becomes a 0. But if you don't tell it whether to be a 1 or a 0, it still has a particular value. We just don't know what it is. So same thing with our memory. The memory always has values. So if I write code like this, it's going to print something essentially random. So let me change this code, and let me put in the following statement, x equals 0. So we're initializing the value of x. All right, what happens when the compiled code gets to this point that says x equals 0? Well, it sees this number 0, and this says copy that into this variable x. Okay, so what is x? It's location 104. That instruction says copy a 0 into location 104. So what does it do? It constructs a number 0 in a temporary location, a bunch of flip-flops, loads a 0 into there, and it says, okay, I'm going to put that into location 104, just like that. And now when we get to the statement which says print the value of x, our code's going to look for the value of x. X is at location 104. It talks to the memory system and says, hey, what's in location 104? The memory system says, let me look. It looks in 104. It says, oh, there's a 0 there. It tells the code that, and the code ends up printing a 0. So that's why if we say x equals 0, print x, we get a 0. All right, so nothing terribly surprising here, but it's important that we understand this level of detail of how memory works, how variables and memory locations are related to each other, so that we can talk about what's next, which is pointers. So let me do one more example of here. Let's make this code a little more interesting, and let's see how this plays out with respect to the memory unit. Alright, so we're going to add some extra code in here. We're going to start off with our x equals 0. We're going to say y equals 5. And then we're going to say x equals y. And then we're going to say z equals x plus y. And then maybe we'll print the value of z down here. I'm not actually executing this code, but I'm just using it, you know, as an example. So let's look what happens as our code runs. Okay, well, we already looked at x equals 0, right? The compiler said, let's put a 0 in location 104, and it already did that, right? There's our 0 in x. All right, let's go to this next statement, y equals 5. Exactly the same thing. Y equals 5 means store a 5 in this location. So the compiler has generated code which will basically create the number 5 in binary somewhere, you know, in a set of flip-flops. And we're storing it in y, so that means put it in location 108. So the CPU talks to the memory unit and says, hey, take this number 5, store it in location 108. And so the memory module, you know, goes to location 108, and it puts that number in there, and now, you know, y is equal to 5. And so, you know, when we write something into memory, it overwrites what was already there. We had a different value there, and now we've got a 5. That other value is lost, even though we can kind of see a little bit of the outline of it. All right, well, now we're at the statement x equals y. So what does this mean? This is going to generate code which does 3 things. It says read the current value of y, and then it's going to take that and put it somewhere, and then it's going to say take that value of y and copy it into x. So that's 2 or 3 things depending on how you look at it. So what's the first step? Read the current value of y. So the CPU talks to the memory system and says, hey, what's at location 108? Because that's the value of y. So the memory system looks and says, that's a 5. All right, so the CPU makes a copy of that value, 5. And then it says, hey, I want to store that in x. Well, where is x? X is location 104. So it takes this 5 and it hands it to the memory unit and says, hey, store this in location 104. And so the memory unit goes to that location and it puts the 5 in there. And that's it. We've just executed this statement, x equals y. So let's do one more statement now, z equals x plus y. All right, we got to do 2 reads, we got to do an addition, we've got to do a write. All right, so we have to read the value of x. X is location 104. Ask the memory unit, what's at location 104? Memory unit says the number 5. And we're going to save that number 5 somewhere. So we're just going to write it down on some scratch pad area. So somewhere, you know, inside the CPU, there's temporary storage that can be used, and it'll write down that value of 5. And then it has to add the value of y. So it's going to ask, you know, what's the value of y? Well, y is at location 108. What's at location 108? Oh, that's also a 5. All right, so it's going to take that value of y and save that. And then it's going to call some kind of add operation in the hardware, right? So if you remember Engineering 250, we looked at the hardware involved in building an adder, right? Well, inside the CPU, there's similar hardware. And by setting the switches correctly inside the CPU, we can take these 2 numbers, this 5 and this 5, and send them to an adder. And so the adder will perform this addition, and 5 plus 5 is 10. And then we're going to say store that in location z. So there'll be another spot somewhere inside the CPU where this number 10 is written in some sense, and it talks to the memory unit and says, hey, store this number at location 112. So the memory module goes to location 112 and it pops the number in there, and we're done. And so now if we come down to this last statement, we say print the value of z, what happens? Well, the code says, hey, tell me what's at location 112. Memory looks at 112, it's a 10, and our code will print out the number 10. Well, that's what it should have done, right? Because we said y equals 5, x equals y, which is also 5, z equals x plus y is 10. This should print a 10. So that's how the 10 gets printed. That's how all of these things work with writing to memory, reading from memory, modifying memory. All right, so that's nothing to do with pointers yet. So let's go ahead and throw pointers into the mix and see how this changes. All right, so I've added a few lines of code here. I've added an integer star p, and we know that star p is our dreaded pointer, right? We're saying that p is a pointer to something. And I've got some print statements. I'm going to print out the value of p, the famous asterisk p, and then asterisk z, just for fun. All right, so first thing I want to stress here is that when you declare a variable, you're really just declaring, you know, something that's going to be stored somewhere in memory. X is an integer, Y is an integer, Z is an integer. P is a pointer, but it's really just another variable. It's a different type of variable. And it's no different from saying, you know, character C or double D variable. Those are just variables, right? If I say character C, what will the compiler do? It will figure out somewhere in memory where it can store C, and it might say, you know, okay, C is going to go at location 117, right? And then if I say double D variable, it might say, okay, I'm going to put that at location 120, right? So these are just variables just like integers. And so what I'm going to suggest is that instead of thinking of integer space star P, think of integer star space P. In other words, move the star over here and just think of this as saying, you know, P is a variable of this type. Just like C is a variable of type car and X is a variable of type int, P is a variable of type whatever this means, int asterisk, right? The compiler doesn't care if I put the star here or over here or if I put it in the middle of all these spaces. But conceptually, it may be easier to think of it as P is just a variable of this type. So I'm going to write it like this, int star space P, and I threw some extra spaces in here just for emphasis. All right, so what happens when the compiler is handed this code? We've already gone through X, Y, and Z. I'm going to stick with those assignments that it came up with. But let's suppose that, you know, for whatever reason it decides, okay, I'm going to store P at location 100, right? I don't know why, but it could decide to do that. So in my table of variables, it's going to say anytime that I want to use the variable P, I'm going to look at location 100. So you remember what happens when we try to access a variable like X, right? We talk to the memory management unit and we say, hey, what's at the location, you know, 104 if that's where X is. So what's going to happen when we say print the value of P? Well, the code that's compiled is going to basically talk to the memory unit and say, hey, tell me what's at location, which location? 100. And so the memory unit will look in location 100 and they'll see, hey, that's the number 108. And so this first print statement would just print out a 108, right? Not too surprising there. All right, the kind of weirdness happens when we get to the second print statement where we're saying print star P. All right, so star P, this is what we call dereferencing our variable P, dereferencing a pointer. And it's almost exactly like this previous statement where we printed the value of P. There's just one extra step, and this one extra step makes all the difference in the world. So when we say print asterisk P, here's what happens. First, the system says, okay, P is at location 100. What's the value at location 100? The memory unit looks at location 100. Oh, it's a 108. Okay, instead of stopping there, now it asks a second question. What's at location 108? Now, why did it ask that? Because it found a 108 in answer to its first question. So P is stored here at location 100. Let's look at the value of P. It's 108. We're not going to print the 108. We're going to do one more step. We're going to say, let's go to location 108. Oh, that's the value 5. Okay, I'm going to print the 5. So this star P means if P equals 100, look in location 100, find 108, look in 108. Right? When we print P, what do we do? If P equals 100, look in location 100. and we just print out that value, 108. But with this star, what it says is, okay, do the same thing you did. P is 100. Go look at memory location 100. What do you find? 108. Go ahead and look at what's at location 108. So it's one level of indirection, right? It's a level of saying, hey, let's now go to location 108 and see what's in there. And when it does that, it sees a 5 and says, okay, I'm going to print a 5. So right now, the value of star P is 5. That's all there is to pointers. But it takes some work to get our brains around that when it's a new concept. But it's a indirect reference. It's saying, hey, don't just stop after you've seen what the value of P is, which is 100. But go one step, P is 108. Don't just stop when you find the value of P. Go one step further and use that value as an address into memory. So this will print 108. This will print what's in box 108. So let me try that as a set of parting comments here. This says print 108, since P equals 108. But down here, this says print what's in box 108. So we do one extra memory reference. That's what the asterisk means. All right, let's look at this last instruction. This says print star Z. So what are we going to do? First thing we're going to do is we're going to look at the value of Z. So what is the value of Z? Well, Z is stored in box 112. So we look in there, and there's the number 10. All right, so do we stop there and print out a 10? No. What we do is we say, okay, let's print what's in box 10, right? So Z is equal to 10. Let's print out the contents of box 10. And so it talks to the memory unit and it says, hey, what do you have in box 10? And the memory unit looks and it says, I don't have a box 10. So what happens? That's a seg fault. And your code says seg fault and it exits and sadness prevails and we have to start debugging. But that's exactly what a seg fault is. You're trying to find what's in a box and there is no such box. And this happens typically if we have a pointer that's pointing to 0 and we ask, well, what's in box 0? And box 0 never exists. In most modern computers, 0 is just not a available memory location. So anytime we try to read box 0, we get a segmentation fault. All right, so that's the basic model of following a pointer or dereferencing a pointer using this asterisk. So let's look at the other direction, which is using the ampersand to find an address. All right, so here's some code where I'm using this ampersand symbol. And we think of ampersand meaning the address of. So when I say P equals ampersand X, what am I saying? Set P to the address of X. Well, what is the address of X? X is stored at location 104. So in this case, if this was the assignments of variables that the compiler came up with, this statement would say P equals 104. And some of this is figured out at compile time, right? We don't have to run the program to know what ampersand X is, because the compiler's already decided where X is going to be stored. It's already decided X is at location 104, so this says P equals 104. So what happens when we run this code? Well, we get down here, this statement says P equals 104. So as we've seen, the number 104 is generated. And P is stored in box 100, so we hand that 104 to the memory unit and say store this in box 100, and the memory unit drops it in there. And now the value of P is 104. And now we come to our next line, which says print asterisk P. And remember how this works. First we look at the value of P is 100. We look in box 100, we see a 104. We're not done. We do one more step, which is look in box 104. And we find a 5. That statement will print out a 5. So this will print the number 5. Now, that number 5, that's also, that's in box 104. That's also the value of x. So in this case, asterisk p means exactly the same thing as x. And we already knew that because we set p to be the address of x. So doing star p in some sense reverses the effect of doing ampersand x. And star p is now just referring to x. So you can think about that. But let's do something else here. Let's add another statement here which says p equals p plus 4, and then let's print asterisk p again. Alright, so how does p equals p plus 4 work? Where is p stored? It's at location 100. Let's see what's in location 100 right now. That's the number 104. Okay, let's take that value, let's add 4 to it. Right, we want to take the current value of p, add 4. So our adder is going to say, let's do 104 plus 4. That's the number 108. So what we're doing here is we're saying p equals p plus 4. We read the value of p, 104. We added 4. We got 108. We need to store that in the variable p. So we take the number 108. And we look at p. P is location 100, so we hand this to the memory unit and say, hey, store this in location 100. And the memory unit goes to location 100, and it stores a 108 in there. Now we do the same print statement we did before. We print star p, and what do we get? Well, what does this mean? It means first, look at the value of p. P is in location 100. What's stored in there? 108. Do one more step. Look in box 108. Oh, there's a 5. Okay, I'm going to print a 5. So that's what that print statement would do. Now if we do this once more, we do another p equals p plus 4. Well, so how is that going to work? Read the current value of p in box 100. That's 108. Add 4 to it. So we're going to do 108 plus 4 is going to give us 112. And we're supposed to store that in p. So we take the number 112. And we hand it to the memory unit and say, hey, store this in location 100. Because that's where p is. So the memory unit goes to location 100 and stores our 112 in there. And now we do the exact same print statement one more time, and we say print the value of star p. So what do? Well, p is in location 100. Let's just look in that box. There's a 112. Not done. Do one more step. Look in box 112. There's a 10. Let's print out a 10. So what happened here? This print statement printed the contents of location 104. This printed the contents of location 108. This printed the contents of location 112. One print statement, but up here it printed the value of x. Here it printed the value of y. Here it printed the value of z. So this is why pointers are powerful, because we can have the exact same code work on different locations in memory. Here we printed the value of x, here we printed the value of z. We didn't have to change this from saying print x to print z. Each of these statements said print star p. But the thing that we ended up printing was different in each case. And we made it different by just manipulating the value of this variable p. So it's almost like we can change what the code does while it's running by just manipulating the value of these pointers. And that's a really powerful feature. Alright, let's go through one more set of code here, and then we're going to talk about arrays. So here I've got my variable x, and I'm saying set x equal to 10. And we're going to stick with the same assignment that the compiler might have come up with. So x equals 10 means put a 10 in location 104. So generate the number 10, hand it to the memory unit, say store this in location 104 please. Go to location 104, store the 10 there. x equals 10. And when we say print x, right, we've done this a number of times now already. The code will say, let's print what's at location 104, and it'll say, hey, memory, what's in location 104, and it'll say that's a 10. So this will print a 10. So let's just make a note here. This prints the number 10. All right, so let's go on to our next step. We're going to say p equals ampersand x. What does that mean? We've done this before. We know that p should be set equal to the address of the variable x. The compiler knows where x is. It knows that x is stored at location 104. So this statement is saying p equals 104. So how do we achieve this notion of setting p equal to 104? Well, we take the number 104. We hand it to the memory unit. P is location 100, and we say store this in location 100. And so the memory unit takes the 104 and puts it in location 100, and we're done. We've set p equal to ampersand x, the address of x. So let me put a note here. For example, now p is equal to 104. All right, so here's the most interesting part. Star p equals 17. All right, so when this star p was on the right-hand side, what did we do? We looked at the value of p, which was 104, and then we said, let's go look in box 104. All right, well, we're going to do the same thing, but in kind of a reverse direction here. Instead of storing 17 in p, which is what we would do if we just said p equals 17, we're going to do one level of indirection. So we've got a 17, right? So the CPU takes, generates the number 17. And where are we going to put it? Well, first we're going to say, where is p? P is in box 100. So we're going to open up box 100, but we're not putting the 17 in there. We're going to see what value is in there. What's that? That's a 104. Okay, we're going to open box 104. That's where we put the 17. All right, very, very subtle difference, but really, really profound. We're going to store 17 in star p. So first we look at the value of p, and p is in location 100, so we look there, but we don't put the 17 in there. We see a 104, that tells us where we're going to store the 17, box 104. What's just happened? Now when we say print the value of x, what's the CPU do? It says x is a 104. What's in box 104? It's a 17. Hey, it prints a 17. So here again, we've got the same statement, just print the value of x, but now this prints 17. So we changed the value of x without actually using x equals anything. In fact, we used the star p equals something, and that's what changed the value of x. So p was a reference to x. And this is why when we do something like we call the scanf function, and we want scanf to load the value of something it found into the variable x, we don't pass x, we pass the address of x. We would pass ampersand x. And the scan function would do something very much like this. It would say, take the thing pointed to by that and set it equal to, whatever it found in your string. So this is also a really useful construct. All right, so let's look at what happens with arrays. So I've got a main program. I have a character array called name. I've declared it to hold 5 elements. And I've got some assignment statements. Name bracket 0 is h, name bracket 1 is I, and name bracket 2 is \0. So we use ASCII codes for storing the values of characters. And so if we look at an ASCII table, we'll see the ASCII code for the letter H is actually 72. And the ASCII code for the letter I is 73. And so let me go ahead and just add some comments in here. This is 72. This is 73. And this \0 is just a shortcut for the ASCII code 0. So that's a way of saying I want to store the number 0 in element 2 of this array. All right, so let's go through our usual drill. Suppose our compiler is working on this code and it sees car name bracket 5. All right, what that means to the compiler is I need to find 5 locations in memory where I can store some information. And they're going to have to be consecutive locations. So we've been jumping by 4s with our integers, but we're going to actually start moving across, and 108, 109, 110, 111, and so on. So suppose that for whatever reason the compiler decides, okay, name, I'm going to store that starting at location 120. All right, so name is going to go at location 120. So we're going to use these memory locations down here at the bottom. So an important thing to know is that when we have an array, the name of that array refers to the location where the array begins in memory. So this 120 is actually the address of name bracket 0. So when we say name bracket 0 equals H, what does the compiler do? The compiled code will take the number 72, that's the ASCII code for H, and it'll say let's store that at location 120. Why? Because that's where name bracket 0 is. So it'll go to location 120, and it'll put the 72 in there. And then it says name bracket 1 equals I. Well, where's name bracket 1? It can figure it out pretty easily because it knows name starts at location 120, and that's where name bracket 0 would be. So the next element of the array, name bracket 1, that's going to be at location 121. And it figures that out by just taking this and adding 1. So it wants to store the letter I, which is ASCII code 73. So it takes that 73, hands it to the memory unit, and says store this in location 121. And so it will do that. And there's our 73 stored in 121. And then this third statement says name bracket 2 equals 0. And where's name bracket 2? Well, this is name bracket 0. Goes right here. Name bracket 1. Name bracket 2 is at location 122. So it takes a 0, hands it to the memory unit, says store this in location 122, and the memory unit does that. So we've just completed these 3 assignment statements. And now we're going to say print out the value of name. All right, so remember what name is. Name is just location 120. Name is actually an address though, right? Name is not equal to the thing stored in location 120. It's not the letter H, it's not the number 72. But the string NAME here means the address where name is stored in memory. So let me put a note on here. The symbol name means location 120 in this case. So when we call this printf function, we don't pass the letter H, we don't pass the letters HI followed by a 0, we pass the number 120, right? We pass the address where this name is stored in memory. So when we call printf, this is what we hand to the printf function. All right, so what does printf do with that? Let me show you what pseudocode might look like for this printf function. All right, so here's some totally high-level pseudocode for how a print function might print a string, a character array like this. So if I've declared this as printf argument, where argument is the number we're passing to it, 120 in this case. And basically it's a loop of 3 statements. Check to see if the thing that argument is pointing to is 0, and if it is, return. You're done. Otherwise, print the character you find at star argument, and then set argument equal to argument plus 1. So that's our 3-step loop here. So when this code is compiled, right, or linked, argument is an integer. It's a pointer actually, but it's a number. It has to get stored somewhere in memory. So let's just suppose that argument is going to be stored at location, I don't know, we'll go with 116. All right, so what happens when we call printf and we pass name? Remember, name is 120. When this code starts executing, that's like saying, okay, I'm going to run this code, and when I'm running this, I want argument to be equal to 120. So what's the compiled code do? It takes the number 120, and it stores it in argument. Well, where is argument? 116. So it hands this to the memory unit, store this in 116. Memory unit pops it in there. All right, so now argument is equal to 116. All right, if star argument is 0, return. So what is star argument? Remember, argument is 116, so look in there. We're not done. That's a 120. Look in 120. That's what star argument is. Right? This is argument. It's got a 120 in it, so this is star argument. So star argument is equal to 72 right now. 72 is not the same as 0, so it won't return. Print the character at star argument. So it prints character 72, and remember, character 72 is the letter H. So our code is going to print out an H. There's our output. And then the last statement of our loop says argument equals argument plus 1. Well, how does that work? Go to location 116. That's where argument is stored. What's in there? It's a 120. Let's add 1 to that. That's going to take our value to 121. Go ahead and store that in location 116. So now this location is equal to 121. And then we go back to the top of the loop. If star argument equals 0, return. So what is star argument? Argument is 116, so look in that box. It's a 121. Let's look in box 121. That's what star argument is. Right? Argument is here. If we wanted to print argument, we would just print 121. If we're looking at star argument, it says, don't stop, it's not 121. Look in box 121. That's what star argument is. It's a 73. That's not 0. So our loop continues, and it says print the character at star argument. Well, star argument is what's in box 121. That's a 73. What does it do when it prints a 73? 73 is the letter I, so it's going to print the letter I. So that gets added to our output. And then our loop says go back to the top. Our loop says argument equals argument plus 1. So argument is stored in location 116. Let's look in there. It's a 121. Let's take that and add 1 to it. So 121 plus 1 takes us to 122. And so we want to store that in argument. So hand it to the memory unit. Hey, store this in box 116. There we go. Argument equals argument plus 1. And now we go back to the top of the loop. And it says if star argument is 0, return. So what is star argument? One more time. Argument is 116, so look in there. There's a 122. Are we done? No. What this means, because it's a star argument, says look in box 122. So go to box 122. Guess what? There's a 0 in there. So star argument is equal to 0. Our pseudocode says, hey, in that case, return. We return to the print statement. We're done. And what was our output? It was HI. And that's what we expected because we stored the letters H and I followed by the null terminator. So that's how, a printf function might work with this pointer that we pass to it when we say, name of the array. We're actually passing the thing that this is pointing to, the place where this is stored in memory, the starting place where it's stored. Or if you like, the address where the first element of the array is stored. So that's how pointers are used to work with arrays. And this is the main reason why pointers are so valuable, because they let us write something like name bracket I, and that will point to a different part of the array depending on the value of I, right? That's the basic function of an array. We can use this index. And the only way that works is because we're not just using a fixed location in memory. We're using a location to tell us the location we should be using. So it's one level of indirection. All right, so that's a pretty high level view of pointers and using ampersands to get addresses of variables and how those two work together, and then how those concepts can work to implement something like an array. So hopefully that helps.